Welcome back to the deep dive. Today, we are taking on, well, probably the biggest questions humanity has ever
And
asked.
arguably the most enduring ones.
Exactly. Where did we come from? And maybe even more important, why is the universe the way it is? Why this specific configuration?
These are really the questions that define not just cosmology and physics, but philosophy too. And for this huge journey, we're drawing from Stephen Hawking's monumental work, A Brief History of Time.
It's the perfect guide, isn't it? Especially with the updates on things like wormholes and time travel. It's not just a history book. It's this incredibly compressed timeline of how we went from thinking we were the absolute center of everything
At the fixed center of creation.
to realizing we're just a tiny, unbelievably complex part of this quantum foam of space-time.
So our mission today is a proper deep dive. We're going to trace centuries of these intellectual revolutions. We'll go from the ancient Greeks all the way to modern string theory.
And we'll be focusing on the huge milestones that completely redefined how we think about space, time, and, well, reality itself.
And to start, you really have to appreciate just how far we've come. Our first models of the universe were based on,
Yeah.
well, on myth and what you could see from your backyard.
I'm thinking of that famous story, the turtles all the way down anecdote. It just perfectly sums up the problem of building your whole cosmology on an assumption you can't prove.
Oh, right. Often attributed to Bertrand Russell. An eminent scientist gives a lecture on the Earth and the planets.
And an old woman stands up at the end and says his theories are, and I'm quoting here, rubbish.
That's it. She says the world is actually a flat plate and it's supported on the back of a giant tortoise.
And the scientist, he thinks he has her. He asks with this little smirk, and what, madam, is that giant tortoise standing on?
To which she replies, completely unfazed, "You're very clever, young man, very clever, but it's turtles all the way down."
And that's the trap, isn't it? The intellectual trap cosmology has been trying to escape. That need for some external foundation, some ultimate turtle.
Exactly. And our journey today is really the story of how observation in mathematics allowed us to replace those infinite turtles with self-consistent laws.
Okay, let's get into it. Let's start right at the beginning of these huge cosmic shifts.
All right, so part one, from a universe centered on us to one held together by gravity.
We should probably start by giving the ancients some credit. This wasn't all just myth.
No, absolutely not. By 340 BC, you have Aristotle presenting these rigorous logical arguments for a spherical Earth. This is long, long before it was widely accepted.
And his reasoning was all based on observation. That's the key, not dogma.
Exactly. For instance, he noted that the Earth's shadow on the moon during a lunar eclipse is always round, no matter how the Earth is turned.
Which would only happen if the Earth was a sphere.
Right. And he also pointed out that the North Star appears lower in the sky when you travel south. If the Earth were flat, it would always be in the same position.
There was also the observation about ships on the horizon seeing the sails first.
All solid observational proof. And he even used this to estimate the Earth's circumference. He was off, he put it at about twice the modern figure. But the fact he could even attempt it based on logic and observation is, well, it's incredible for that time.
So, okay, by 340 BC, we know the shape is a sphere, but the position is still fundamentally wrong.
And that brings us to the model that dominated Western thought for over 1,300 years. Ptolemy's geocentric system from the 2nd century AD.
Earth at the very center of everything.
Stationary, dead center. And around it, he imagined these 8 nested crystalline spheres. One for the moon, one for the sun, one for each of the 5 known planets.
And then the final outermost sphere for all the fixed stars.
It's a very satisfying picture. It's neat, it's organized, it revolves around us.
But tidy models rarely survive contact with messy reality, do they?
They do not. The planets
Yeah.
just didn't move in perfect circles. Astronomers could see that. Sometimes they even appeared to slow down, stop, and move backward for a bit.
Retrograde motion.
Right. So to save the model and to preserve this mystical idea of perfect circular motion, Ptolemy had to add these complications.
Epicycles. The smaller circles on top of the bigger circles.
Exactly. It became this incredibly complex, clockwork-like system, but it was all just a patch to make the theory fit the data. And it led to some really obvious problems.
The source points out a huge one with the moon, right?
A glaring one. To make his model accurately predict the moon's position, Ptolemy's math required the moon to sometimes be twice as close to the Earth as at other times.
If that were true, it would look twice as big in the sky sometimes, which it obviously doesn't.
And Ptolemy knew it. He acknowledged the inconsistency himself.
So why did it stick for so long? I mean, 1,400 years with a known visible flaw.
Well, partly because it worked well enough for predicting positions, But also, and this is crucial, it had metaphysical utility. It fit the prevailing worldview.
It put humanity and Earth at the center of the cosmic drama.
Yes, and as Hawking notes, it left a room outside the sphere of fixed stars for heaven and hell. It was comforting, and sometimes comfort is more powerful than consistency.
Until Copernicus, 1514.
The Copernican revolution.
Mhm.
He proposed a much, much simpler model. Just put the sun at the center, stationary, and have the Earth and planets orbit it.
Which was a huge deal. He was so worried about the reaction, he circulated it anonymously at first.
It took people like Galileo and Kepler to really champion it. Galileo, with his telescope in 1609, saw moons orbiting Jupiter. That was definitive proof that not everything in the universe orbited the Earth.
A stake through the heart of the geocentric model.
And then Kepler provided the final, crucial mathematical fix. See, Copernicus still clung to the idea of perfect circles. It was Kepler who realized the orbits weren't circles at all.
They were ellipses.
Ellipses. And once he made that change, the model finally perfectly matched the centuries of observational data.
So, by the 17th century, the picture is right sun in the middle, planets in elliptical orbits, but it's still just a description. It says what is happening, but not why.
And that is the giant leap that Isaac Newton makes in 1687 with his Principia Mathematica.
This is the moment we get a mechanism. We get laws.
Universal laws. His first law of motion just completely demolishes Aristotle's idea that an object's natural state is rest. Newton says no, the natural state is perpetual motion in a straight line.
It only stops or changes direction if a force acts on it.
And his second law tells you how that works. Force is mass times acceleration. Simple, powerful.
But the real masterpiece was the law of universal gravitation.
The idea that every single body in the universe attracts every other body, with a force that depends on their mass and the distance between them.
And suddenly, the heavens and the earth are governed by the exact same law. The force that keeps the moon in orbit is the same force that makes an apple fall from a tree.
Which brings us to the famous apple story. Probably not true in the literal sense, but Newton himself said the idea came to him while he was in a contemplative mood.
It's a great story because it captures that unification perfectly. And his law also explains something Galileo had noticed but couldn't really explain.
Right, why all objects fall at the same rate, regardless of how much they weigh.
So a feather and a cannonball fall at the same speed, ignoring air resistance.
Newton's law explains it perfectly. A heavier object feels a stronger gravitational pull, yes. But its greater mass also means it has more inertia. It resists being accelerated more.
And the two effects cancel each other out exactly.
Precisely. It was a beautiful, deterministic clockwork universe. You could predict everything. But that very perfection had some deep, hidden cracks that would eventually bring the whole system down.
Which brings us to part 2, the complete reimagining of space and time.
And the death of the absolute.
Okay, so the first crack in this perfect Newtonian clockwork was, well, it was a subtle one. It was this idea that there's no such thing as absolute rest.
Right. We touched on it with his laws of motion. If you're on a train moving at a perfectly constant speed and you drop a ball, it falls straight down, just like it would if you were standing still on the ground.
You can't do any experiment inside the train to prove you're moving. All the laws of physics are identical.
Which means there is no absolute at rest. Motion is only ever relative to other things. You're at rest relative to the train, but moving relative to the ground.
This apparently bothered Newton a lot.
Deeply. He was a very religious man, and the lack of an absolute space, a fixed divine frame of reference, seemed to conflict with his idea of an absolute God.
And it opened him up to all sorts of philosophical attacks, like from Bishop Berkeley. But the thing that really broke the system wasn't philosophy, it was light.
And the first clue came even before Newton published his Principia. A Danish astronomer, Ole Romer, in 1676.
He was watching the moons of Jupiter, right, using them like a cosmic clock.
Exactly. He noticed that the eclipses of Jupiter's moons seemed to happen later when the Earth was on the far side of its orbit from Jupiter.
Farther away.
Right, and he correctly deduced that it was because the light from those moons was taking longer to reach us across that extra distance.
Which meant light doesn't travel instantaneously, it has a finite speed.
A revolutionary idea. His estimate was a little low, around 140,000 miles per second, but the concept was the critical thing.
And then, much later, in 1865, James Clerk Maxwell unified electricity and magnetism.
And his equations predicted that light was an electromagnetic wave that traveled at a very specific fixed speed, the speed we now call $.
Okay, but a fixed speed relative to what? If there's no absolute space, what is light speed fixed against?
Well, 19th century physicists had to invent something. They called it the ether. This was supposed to be a massless, invisible, stationary substance that filled all of space, and it was the medium through which light waves traveled.
Like sound traveling through air.
Precisely. And if this ether exists, and the Earth is moving through it, then we should be able to measure our motion relative to it.
You'd expect the speed of light to look different if you're measuring it in the direction of the Earth's motion versus perpendicular to it, like running into a headwind versus a crosswind.
Exactly. And that set the stage for one of the most important failed experiments in history, the Michelson-Morley experiment in 1887.
They built an incredibly precise device to measure exactly that difference, to detect this ether wind.
And they found nothing.
No difference at all.
The speed of light was exactly the same no matter which direction they measured it. It was completely invariant.
Which completely destroyed the idea of the ether, so physics was in a total crisis.
A huge crisis.
Yeah.
How could the speed of light be constant if there was nothing for it to be constant relative to?
Enter Albert Einstein, 1905.
And he comes along with this incredibly bold, revolutionary postulate. He just says, let's abandon the ether. Let's start from what the experiment tells us. The laws of science, and especially the speed of light, must be the same for all observers who are moving freely, no matter how fast they're going relative to each other.
That one simple idea solves the Michelson-Morley problem instantly.
It does, but the consequences, the price you have to pay for that solution is you have to throw out the idea of absolute time and absolute space.
Because if the speed of light is the constant, something else has to change to make the math work.
Space and time themselves have to become flexible. They have to stretch and shrink depending on your motion.
This leads to some monumental consequences. The first is pretty famous. Nothing can travel faster than light.
And the reason for that is the second consequence, the famous equation, Ibn 2 Mass and energy are equivalent.
So as you try to accelerate an object closer to the speed of light, the energy you pump into it doesn't just make it go faster.
It also adds to its mass, gets heavier. And the closer you get to the speed of light, the more massive it becomes, until at the speed of light, its mass would be infinite.
You'd need infinite energy to get it there. It's an unbreakable speed barrier.
And the third consequence is the most mind-bending. The idea of now becomes relative. Two events that are simultaneous for me might not be simultaneous for you if you're moving relative to me.
So space and time aren't separate things anymore.
They're woven together into a single four-dimensional fabric, space-time. To locate any event, you don't just need 3 space coordinates, left, right, forward, back, up, down. You also need a time coordinate.
It's hard to visualize 4 dimensions.
It is, but you can think of it by analogy. The surface of the Earth is a curved 2D space. You can't separate north-south from east-west. Space-time is a 4D version of that.
Okay, so this is special relativity. But it only deals with constant motion. What about gravity? Gravity is an acceleration.
That took Einstein another 10 years. In 1915, he published his theory of general relativity. And in it, he completely redefined gravity.
So it's not a force pulling things together anymore.
No. He proposed that gravity is a consequence of the geometry of space-time itself, mass and energy warp or curved space-time.
So a huge object, like the sun, creates a kind of dip in the fabric of space-time.
Exactly. And a planet like the Earth isn't being pulled by an invisible force. It's just following the straightest possible path, a geodesic, through that curved space.
And that straight path in curved space looks to us like a circular orbit.
Precisely. And this new theory made some very specific, testable predictions that Newtonian physics just couldn't account for.
The first one was small but nagging. The orbit of Mercury.
Yes. Mercury's elliptical orbit slowly rotates, or precesses, over time. Newton's laws were very, very close to predicting it, but not quite. Einstein's theory of curved spacetime nailed the prediction perfectly.
But the big one, the one that made him famous, was about light.
He predicted that light itself should be bent by gravity. A ray of light passing near a massive object like the sun should follow the curve in spacetime.
Which was tested in 1919 during a solar eclipse.
Yes, a British expedition led by Arthur Eddington went to West Africa. During the eclipse, they photographed the stars near the sun's edge and compared their positions to where they normally are.
And the starlight had been deflected, exactly as Einstein predicted.
It was a huge moment, a British team confirming a German scientist's theory right after World War I. It made headlines around the world. Though the source does note with a bit of irony that the experimental errors were pretty large, and it's possible they knew the result they wanted to get.
But later, more accurate measurements confirmed it beyond any doubt.
And we can't forget the last piece, which has huge practical consequences for us today. Time dilation.
Clocks run at different speeds depending on gravity.
General relativity predicts that time should appear to run slower, closer to a massive body. The stronger the gravity, the slower time passes.
And this isn't just a theory, it's been measured.
Oh, absolutely.
Mm.
In 1962, they put two extremely accurate clocks, one at the bottom of a water tower and one at the top. The one at the bottom, closer to the Earth's mass, ran measurably slower.
And this is critical for GPS, right?
It's essential. The GPS satellites are in orbit where gravity is weaker, so their clocks run slightly faster than ours on the ground. It's only a tiny fraction of a second per day, but if the system didn't constantly correct for that relativistic effect, the positioning errors would build up at a rate of several miles per day.
Incredible. So general relativity gives us this dynamic, curved universe. But Einstein himself made a mistake here. He missed the biggest implication of his own theory.
He did. He thought the universe had to be static, stable. He couldn't accept that his own equations were pointing to something else entirely.
That the universe is expanding.
Which is where our story goes next.
All right, part 3, the expanding universe, the Big Bang, and where it all began. First, we need to just get a sense of the scale we're talking about.
The scale is almost incomprehensible. Our sun is 8 light minutes away. The next nearest star, Proxima Centauri, is 4 light years away.
And we're just one star in our galaxy, the Milky Way.
One of about 100 billion stars in a spiral disk that's 100,000 light years across.
But the real shock came in 1924. Before then, we thought our galaxy was basically the whole universe.
Right, those little fuzzy spiral patches we saw in telescopes were just called nebulae. But Edwin Hubble proved they weren't inside our galaxy at all.
How did he do that?
He used a type of star called the Cepheid 8 variable as a standard candle. These stars have a known, predictable brightness. By measuring how dim they appeared in those nebulae, he could calculate their distance.
And they were millions of light years away. They were entire other galaxies.
Suddenly, the universe wasn't just our galaxy. It was a universe of hundreds of billions of galaxies. But Hubble's most famous discovery came 5 years later, in 1929.
When he was looking at the light from these distant galaxies.
Exactly. He was using a spectroscope to look at their light spectra, the rainbow of colors with dark lines where elements absorb specific frequencies.
Like a chemical fingerprint.
Right. And he noticed something astonishing. For almost every distant galaxy, those fingerprints were shifted. They were moved toward the red end of the spectrum.
This is the Doppler effect.
For light. Just like the siren of an ambulance sounds lower in pitch as it moves away from you, the light from an object moving away from you is stretched to a longer, redder wavelength.
And the conclusion was staggering.
Nearly all galaxies are moving away from us, and the farther away a galaxy is, the faster it's moving away. The entire universe is expanding.
This one discovery it solved so many problems at once.
It did. For one, it explains why the universe hasn't collapsed under its own gravity, a problem that should have worried Newton.
And it also solves Olber's paradox, right? The question of why the night sky is dark.
Exactly. The paradox from 1823 says that if the universe were infinite, static, and it existed forever, then no matter where you looked in the sky, your line of sight would eventually end on the surface of a star.
The whole night sky should be as bright as the sun.
But if the universe is expanding, the light from the most distant stars is redshifted so much it's no longer visible, or it simply hasn't had enough time to reach us yet.
It's amazing that even Einstein resisted this idea at first.
He did. He believed so strongly in a static universe that he actually added a fudge factor to his equations to force them to be stable. He called it the cosmological constant.
An anti-gravity force, basically.
Yes. He later called it the biggest blunder of his life after Hubble's discovery. The person who really took the equation seriously from the start was a Russian physicist, Alexander Friedmann.
And he came up with models for a dynamic, non-static universe back in the 1920s.
He did. And his models gave us the 3 possible fates for the universe, and it all comes down to one number, the average density of matter and energy.
Okay, what are the 3 scenarios?
Scenario 1. There's a lot of matter. The density is high, so gravity is strong enough to eventually stop the expansion and pull everything back together in a fiery collapse.
The big crunch.
Scenario 2.
Yeah.
The density is exactly at a critical value. Gravity is just strong enough to slow the expansion down forever, but it never quite stops it. It just sort of coasts to a halt over infinite time.
And the third.
The density is too low. Gravity isn't strong enough to ever stop the expansion. The universe just expands faster and faster forever.
The key insight here is that if the universe is expanding now, then in the past it must have been smaller.
And if you run the clock all the way back about 13.8 billion years ago, everything, all the matter, all the energy, all of space itself must have been compressed into an infinitesimally small, infinitely dense, infinitely hot point.
The Big Bang singularity.
And this was a monumental shift. The question of creation, of the beginning of the universe, was no longer just for theology or metaphysics. It was now a question for physics.
Because at that singularity, all our known laws of physics break down. Time itself must have begun there.
Understandably, a lot of scientists hated this idea. They tried to find ways around it. The most famous alternative was the steady-state theory.
Which proposed that the universe was expanding, but new matter was constantly being created out of nothing to fill the gaps so it always looked the same.
That theory was eventually disproved by observations. For one, we saw that the universe looked different in the past. There were more quasars, for example.
But the real killing blow was the discovery of the echo of the Big Bang itself.
The final proof came in 1970, when Roger Penrose and Stephen Hawking published the singularity theorem. It was a mathematical proof that, if general relativity is correct, a singularity like the Big Bang is unavoidable.
And then came the observational evidence. The smoking gun.
By complete accident, in 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were using this big sensitive antenna.
And they kept picking up this annoying, persistent background hiss, a microwave noise.
It came from every direction, day and night, season after season. They tried everything to get rid of it. They famously even scraped pigeon droppings out of the antenna, thinking that might be the source.
But the noise wouldn't go away.
Meanwhile, just down the road at Princeton, a team of physicists led by Robert Dicke had predicted that if the Big Bang really happened, the universe would have started out as a glowing, white-hot fireball.
And as the universe expanded, that intense light would have been stretched, redshifted, all the way down into the microwave part of the spectrum.
It would be a faint, uniform glow coming from all directions,
Whoa.
a fossil remnant of creation.
And that's exactly what Penzias and Wilson had found by accident, the cosmic microwave
It
background.
was the definitive confirmation of the Big Bang.
So that brings us back to the big question. Which of Friedman's models are we in? What's the fate of our universe?
It all comes down to density. If we add up all the visible matter, all the stars and galaxies we can see, we get less than 1% of the density needed to stop the expansion.
But we know there's more out there. Dark matter.
Right. We can see its gravitational effects holding galaxies together.
Yeah.
But even when we add up all the inferred dark matter, we still only get to about 1/10 of the critical density.
So based on that evidence.
It seems the universe will expand forever. Now, we should note that since these sources were written, the discovery of dark energy has shown the expansion is actually accelerating, which strengthens that conclusion.
But either way, the evidence points away from a big crunch.
It does.
Okay, so that sets the stage on the cosmic scale. Now we have to zoom in, way in, to the realm where all the certainty of Newton and Einstein just falls apart.
The world of quantum mechanics.
Let's move into part 4, where predictability itself comes into question.
For a couple of centuries after Newton, physics was built on this idea of scientific determinism. The French mathematician Laplace summed it up best.
Right, the idea that if you knew the exact position and speed of every single particle in the universe at one instant,
You could, in principle, calculate the entire future and the entire past of the universe. A perfect clockwork machine.
it's a powerful idea, but it was doomed. And not by philosophy, but by physics itself.
Classical physics just broke down when it tried to explain certain things.
Yeah.
A key one was how hot objects radiate energy. The equations predicted that a hot body, like a glowing piece of metal, should radiate infinite energy, which is obviously wrong.
The ultraviolet catastrophe.
Exactly. And the solution, proposed by Max Planck in 1900, was the birth of quantum theory. He suggested that energy isn't continuous. It comes in discrete little packets, or quanta.
And that idea opened a Pandora's box. The next big shock was Heisenberg's uncertainty principle.
This was the final, fatal blow to Laplace's deterministic dream. Heisenberg showed that there is a fundamental limit to what we can know.
You can never know both the exact position and the exact momentum or velocity of a particle at the same time.
The more precisely you measure one, the less precisely you know the other. It's not a limit of our instruments. It's a fundamental property of nature. Complete knowledge of the present is physically impossible.
Which makes predicting the future with certainty also impossible.
And this weirdness is rooted in something even stranger. Wave-particle duality.
Everything in the universe has properties of both a particle and a wave.
Light, which we think of as a wave, can act like a particle of photon. An electron, which we think of as a particle, can act like a wave.
And the classic experiment that shows this is the two-slit experiment.
If you fire waves, like water waves, through two slits in a barrier, they spread out and interfere with each other, creating a distinct pattern of peaks and troughs on the other side.
An interference pattern.
Right. Now, if you fire tiny particles, like marbles, at the slits, you'd expect just two bands behind the slits where they went through.
But when you do this with electrons,
You get an interference pattern, as if each electron were a wave.
and here's the truly bizarre part. Even if you fire the electrons one at a time, so they can't possibly be interfering with each other,
They still, over time, build up that same interference pattern.
the only way that can happen is if each individual electron somehow goes through both slits at the same time and interferes with itself.
It's a conclusion that just seems to defy all common sense. It suggests a particle doesn't have a single, definite path.
And this leads to Richard Feynman's incredible idea of the sum over histories.
Right. To get from point A to point B, a particle doesn't take one path. It takes every single possible path all at once.
All of them. The straight path, the curvy path, the path that goes to the moon and back.
All of them. And the final outcome we observe is a sort of weighted average, a sum of all those possible histories. For big objects, most of the weird paths cancel each other out, and you're left with the familiar classical path. But for a single electron, all those possibilities are real.
So reality at the quantum level is just a haze of probabilities.
A probabilistic cloud of potential realities, yes. And the building blocks of matter itself are governed by this. We now know that protons and neutrons aren't fundamental. They're made of even smaller particles called quarks.
Up, down, strange, charmed, bottom and top.
And they're held together by the strong nuclear force, which has these two really weird opposite properties.
The first is called confinement.
You can never, ever see a quark by itself. If you try to pull two quarks apart, the force between them gets stronger, not weaker. It's like stretching a rubber band that never breaks.
But the second property is the exact opposite.
Asymptotic freedom. At really, really high energies, like inside a particle accelerator or in the very early universe, the strong force gets incredibly weak, and the quarks act almost like free particles, just rattling around.
So we have this transition from a rigid, predictable world on our scale to this fuzzy, probabilistic world on the smallest scales.
And the place where those two worlds collide with the most spectacular results is inside a dying star.
Okay, let's go there. Part 5. Black holes, where gravity and quantum mechanics have their ultimate showdown.
First, we need the basics of a star's life. A star is a constant battle between gravity, which wants to crush it, and the outward pressure from nuclear fusion in its core.
It's burning hydrogen into helium, creating massive amounts of energy.
Right. And for most of its life, those two forces are in perfect balance. But eventually, the fuel runs out. And when it does, the star cools, the pressure drops, and gravity starts to win.
And what happens next depends entirely on the star's mass, specifically whether it's above or below the Chandrasekhar limit.
A young physicist named Subrahmanyan Chandrasekhar calculated this in 1928. He figured out the maximum mass a star could have and still support itself against gravity once its fuel was gone.
What's holding it up at that point?
A quantum mechanical rule called the Pauli exclusion principle basically says that two identical particles, like electrons, can't be squeezed into the exact same state. This creates a powerful repulsion pressure.
And the limit he found was about 1.5 times the mass of our sun.
Right. If a dying star's core is below that mass, the electron repulsion pressure is strong enough to stop the collapse. The star shrinks down to about the size of the Earth and becomes a super dense object called a white dwarf.
But if it's above that limit,
Chandrasekhar's math showed that the electron pressure would fail. Gravity would be so strong that it would just keep crushing the star down to an infinitely dense point, a singularity.
the scientific establishment at the time hated this idea.
Hated it. The great Arthur Eddington publicly ridiculed him. Even Einstein thought some unknown law of physics must step in to prevent such a catastrophe.
But Chandrasekhar was right. We now know there's a second possible stable state, a neutron star, where the collapse is halted by the repulsion between neutrons. They're even denser. A whole star crushed into the size of a city.
But for the most massive stars, even that isn't enough. The collapse is unstoppable. And it creates a black hole.
Which is defined by two things: the singularity at the center
And the event horizon. This is the boundary around the singularity. It's the point where the gravitational pull becomes so strong that the escape velocity is greater than the speed of light.
The point of no return.
Once you cross it, you can never get out. Not even light can escape. The source quotes Dante, "All hope abandon, ye who enter here."
So if they're black, if they emit no light, how on earth do we find one?
We look for their gravitational effects on things around them. The best place to look is in a binary star system, where a visible star is orbiting an unseen companion.
And the classic example is Cygnus X1.
A very powerful source of X-rays. The idea is that there's a normal star and a black hole orbiting each other. The black hole's gravity is pulling gas and material off its companion star.
And as that gas spirals in towards the black hole,
It gets accelerated to incredible speeds, heats up to millions of degrees, and emits a flood of X-rays right before it crosses the event horizon and disappears forever.
and by looking at the orbit of the visible star, we can calculate the mass of its invisible partner.
And in the case of Cygnus X1, the companion is at least 6 times the mass of the Sun. Far too massive to be a white dwarf or a neutron star. It has to be a black hole.
This is what finally made Hawking concede his famous bet with Kip Thorne.
Right. He had bet that Cygnus X1 was not a black hole, as a kind of insurance policy. He figured if black holes didn't exist, at least he'd win the bet.
But the evidence became too overwhelming.
Exactly. We now know there are stellar mass black holes like this all over the galaxy. And there are also supermassive black holes at the centers of most galaxies, including our own.
Some of them are billions of times the mass of the sun.
Right. And they're the engines that power quasars, the brightest objects in the universe. But the most radical idea about black holes came in 1973, when Hawking realized that when you apply quantum mechanics to them,
Black holes ain't so black.
they're not completely black. They should glow faintly. They should radiate energy.
And this comes directly from the uncertainty principle, the idea that empty space isn't really empty.
It's fizzing with activity. Pairs of virtual particles and antiparticles are constantly popping into existence, borrowing energy from the vacuum, and then annihilating each other a moment later.
But what happens if a pair of these virtual particles pops into existence right at the edge of a black hole's event horizon?
Well, it's possible for one of them to fall in while the other escape.
And to an outside observer, it would look like the black hole just emitted a particle.
Exactly. The key is that near a black hole, a particle can have negative energy. So the particle with negative energy falls in, which reduces the black hole's total mass and energy, and its positive energy partner flies away as real radiation.
So the black hole is slowly losing mass. It's evaporating.
Very, very slowly for a big one. A solar mass black hole would take longer than the current age of the universe to evaporate. But the smaller the black hole, the hotter it is, and the faster it radiates.
And this opens the possibility of finding tiny primordial black holes.
If tiny black holes were formed in the chaos of the Big Bang, ones with the mass of a mountain but the size of an atom, they would be radiating energy away at a tremendous rate right now.
They'd be white hot.
And they would end their lives in a massive explosion, a final burst of gamma rays with the energy of millions of hydrogen bombs. Detecting one of those final flashes would be incredible proof of both primordial black holes and Hawking radiation.
So this is where general relativity and quantum mechanics are forced to talk to each other. And it shows that we need a theory that unites them.
We need a theory of everything, a grand unified theory.
Okay, let's talk about that quest, part 6, the search for the ultimate theory.
The whole goal of modern physics, really, is to find a single theory that explains everything. One that unifies the 4 fundamental forces of nature into a single underlying principle.
Let's just quickly review those 4 forces.
Okay, from weakest to strongest. First, you have gravity. It's incredibly weak, but it's long range and always attractive, so on the scale of planets and galaxies, it dominates.
Second, the electromagnetic force, carried by the photon.
Much, much stronger than gravity. But it can be attractive or repulsive, so on large scales, positive and negative charges tend to cancel each other out.
Third, the weak nuclear force.
This one is responsible for certain types of radioactivity. It's very short range, and it's carried by massive particles called W and Z bosons.
And finally, the strong nuclear force, the strongest of all.
Carried by the gluon, and it's a force that binds quarks together to make protons and neutrons. Also extremely short range.
The first major success in unification came in the 1960s.
The Weinberg-Salam theory, which unified the electromagnetic force and the weak force. It showed they are actually 2 different aspects of a single force, the electroweak force.
And this relies on an idea called spontaneous symmetry breaking. What does that mean?
The idea is that at very high energies, like in the early universe, the two forces were identical, perfectly symmetrical. But as the universe cooled, that symmetry broke.
A bit like a pencil balanced on its point. It's perfectly symmetrical, but it's unstable. It has to fall in some random direction, breaking the symmetry.
That's a great analogy. As the symmetry broke, the W and Z particles acquired mass, making the weak force short range, while the photon remained massless, keeping the electromagnetic force long range.
So the next step is a grand unified theory, or GUT, that also includes the strong force. And these theories, if they're right, could solve one of the biggest mysteries of all.
The matter-antimatter asymmetry.
Why is there anything here at all?
Exactly. Physics tells us that for every particle, there's an antiparticle with the opposite charge. When they meet, they annihilate into pure energy. The Big Bang should have created equal amounts of both.
In which case, everything should have annihilated everything else in the first second, leaving behind a universe filled with nothing but light. No stars, no us.
But we're here, which means there must have been a tiny imbalance, a slight excess of matter over antimatter.
And GUTs provide a way for that to happen.
Yes, they predict that at the stupendously high energies of the early universe, quarks could turn into other particles, like anti-electrons. But for an imbalance to be left over, the laws of physics themselves can't be perfectly symmetrical.
There has to be a slight preference for matter.
Specifically, they need to violate something called CP symmetry, a combination of charge reversal and mirror image reversal. And we know from experiments in 1964 that this violation actually happens.
So this tiny, subtle flaw in the symmetry of the laws of nature is the reason we exist.
It seems so. A slight preference for quarks over antiquarks in the early inferno meant that after all the annihilation, a small residue of matter was left over, about 1 quark for every billion photons.
And that 1 in a billion leftover is everything we see.
It is. Now, the final biggest hurdle is bringing gravity into the fold.
Because general relativity is a classical theory, and the others are quantum theories.
And when you try to combine them, you get mathematical nonsense. The quantum fluctuations of space itself, the virtual particles, have infinite energy, which would mean space-time should be curled up into an infinitely small ball, which it clearly isn't.
This is where string theory comes in.
It's the most promising and most controversial candidate for a final theory. The radical idea is that the fundamental entities in the universe are not zero-dimensional points.
They're tiny, one-dimensional vibrating strings.
And what we see is different particles, an electron, a quark, a photon, are just different vibrational modes of this same fundamental string, like different notes played on a violin string.
It's an elegant idea. All the particles and forces are just different tunes.
And one of those vibrational modes, one of those notes, has the exact properties of the graviton, the quantum particle of gravity. So gravity is naturally included in the theory.
But there's a huge catch.
A very big one. The math of string theory only works if space-time has more dimensions than the 4 we see.
10 or 11, or even 26 in some early versions.
So where are they? The proposed solution is that the extra dimensions are curled up or compactified on an incredibly small scale.
So small we could never possibly detect them.
Like looking at a garden hose from a great distance. It looks like a one-dimensional line. But if you get up close, you see it has a second dimension, its circumference. The extra dimensions of string theory are like that, but curled up to a size of a billion trillion trillionth of a centimeter.
That seems convenient. But it raises the question, why did our universe end up with 3 big space dimensions and 1 of time?
And for that, we turn to the anthropic principle.
The idea that the universe must be the way it is, because if it were different, we wouldn't be here to observe it.
And there are some surprisingly strong arguments for why our 3 plus 1 dimensional universe is special.
What's wrong with fewer dimensions?
Well, in a 2D world, life as we know it would be impossible. An animal with a digestive tract that goes all the way through its body would simply fall into 2 pieces. Complex nervous systems would be impossible to wire without connections crossing.
And more dimensions.
That's even worse. The problem is gravity. In 3 dimensions, gravity follows an inverse square law. If you had 4 space dimensions, it would be an inverse cube law.
It would get weaker, faster with distance.
Which means stable orbits for planets around stars or electrons around nuclei would be impossible. Everything would either fly apart or spiral into the center. No stable atoms, no stars, no life.
So we live in a 3 plus 1 dimensional universe because it's the only kind that can support complex, stable structures like us.
That's the argument. Our existence itself selects the kind of universe we can observe.
So we're getting to the very edge of physics here, which seems like a good place to talk about the final frontiers. time travel, the beginning of time, and the ultimate nature of reality.
Right, part 7.
Let's start with the one everyone wants to know about, time travel.
Relativity makes a very clear connection. If you could travel faster than light, you could also travel back in time. The two are inextricably linked.
But we already established that the energy required to reach light speed is infinite, so that's out.
For a conventional rocket, yes.
Hmm.
But the other theoretical possibility is to warp space-time itself,
Yeah.
to create a shortcut,
A wormhole.
an Einstein-Rosen bridge, a tunnel connecting two distant points in space-time. You could, in theory, step through it and emerge instantly, millions of light years away, or at a different time.
What's the catch? Because there's always a catch.
The catch is that to keep a wormhole open, you need to prop it open with something that has negative energy density, exotic matter.
Something with anti-gravity.
Essentially, yes.
Yeah.
In classical physics, that's impossible. Energy and mass are always positive. But in quantum mechanics,
The uncertainty principle allows for it.
exactly. The Casimir effect is a real measured example. If you put two metal plates very close together in a vacuum, the region between them has slightly less of the virtual particle fizz than the space outside. Relative to the outside, the energy density between the plates is negative.
So, in principle, the physics to stabilize a wormhole exists.
In principle. But then you have to deal with the paradoxes. If you go back in time and kill your grandfather, how were you ever born to do it?
The source mentions two possible resolutions.
The first is the consistent histories idea. The laws of physics would conspire to prevent you from changing the past. Your gun would jam, you'd miss, something would happen. The past is fixed.
The second is the alternative histories idea.
The Back to the Future model. When you go back, you enter a new parallel timeline, and your actions create a different future in that branch without affecting your own original history.
It's all very speculative, but the source makes a fascinating point. Time travel is already happening on a microscopic scale.
Right? The Hawking radiation process can be seen as an antiparticle traveling backward in time out of the black hole. So maybe the laws of physics don't forbid travel to the past, but something prevents it on a large scale.
The chronology protection conjecture. As Hawking puts it, the best evidence we have that time travel is not possible is that we haven't been invaded by hordes of tourists from the future.
Which brings us to the ultimate question this all leads to, the beginning. The Big Bang singularity. What were the initial conditions of the universe?
This is where we need a theory of quantum gravity. And this is where the no-boundary proposal comes in.
It's a way of using Feynman's sum over histories for the entire universe. But to make the math work, you have to use a mathematical trick called imaginary time.
What is imaginary time?
It's a mathematical concept where time behaves just like another dimension of space. There's no longer a fundamental difference between forward and backward in time, just like there's no difference between left and right in space.
So if you model the history of the universe in this imaginary time, what does it look like?
It looks like the surface of a sphere. It starts at a point, the North Pole, with zero size. It expands to a maximum size at the equator, and then it recontracts to a point at the South Pole.
And the crucial part.
The crucial part is that the North Pole is just a smooth point on the surface. It is not a singularity. The laws of physics hold everywhere.
So in imaginary time, the universe has no beginning, no edge, no boundary.
It is completely self-contained. It simply is. Now, when you translate back into the real time that we experience, the singularity at the beginning reappears. But its nature is determined by this smooth, boundaryless condition in the underlying quantum reality.
And this idea also explains the arrow of time, why time moves forward.
Right. The laws of physics themselves don't really care about the direction of time. But we experience three arrows of time all pointing in the same direction.
The cosmological arrow, the universe is expanding. The thermodynamic arrow disorder, or entropy, is always increasing. And the psychological arrow, we remember the past, not the future.
The no-boundary proposal suggests the universe began in a very smooth, simple, highly ordered state. As it expands, it must get more disordered. And intelligent life, which requires consuming ordered energy, food, and creating disordered energy, heat, can only exist when this thermodynamic arrow is strong.
So we must find ourselves in the expanding phase of the universe, where all three arrows point in the same direction.
Our existence is linked to the arrow of time.
The conclusion here is it's staggering. If the universe is completely self-contained with no boundary, then in this deeper sense, it had no beginning and will have no end. It would simply be.
Determined entirely by the laws of science.
Okay, let's try to wrap this up. We have gone from a flat Earth on the back of a turtle
to a self-contained, 10-dimensional quantum universe
Yep.
that may have had no beginning. The intellectual journey is just immense.
It is. And the quest continues. The search for that single, complete, unified theory that doesn't need any arbitrary numbers plugged in to make it work.
But we have to be humble. The source reminds us of all the false dawns in physics. In 1928, Max Born said he thought physics would be over in 6 months.
And then they discovered the neutron and the nuclear forces, and the whole field exploded again.
Exactly. This pursuit has also shifted who gets to ask the big questions. For centuries, why are we here was a question for philosophers. Now, the answer seems to lie in incredibly technical mathematics that few can understand.
But the question itself hasn't changed. Why does the universe go to all the bother of existing?
What is it that breathes fire into the equations and makes a universe for them to describe?
And that brings us to the final, provocative thought. The question Einstein asked, how much choice did God have in constructing the universe?
If the no-boundary proposal is right, then maybe God had no choice at all when it came to the initial conditions. They were fixed by the laws of physics.
The only choice was in the laws themselves.
And the final stunning implication is that there might only be one single, unique, self-consistent, unified theory that is mathematically possible and also allows for the existence of complex structures like us.
If we were to find that one unique law, we would, in a very real sense, know the mind of God.
Something for you to mull over.
Until our next deep dive, thank you for joining us.